Right. So yesterday we talked about, well, we started chapter 3. So we wrapped up the Laplace transform. Maybe a quick recap on Laplace transform. We use Laplace transform as a tool. It turns the system from the time domain into the complex frequency domain, where it's a linear operation, and we use that to turn a differential equation into a, I guess, algebraic equation. Then we solve for it. Then we take the inverse Laplace transform to get the solution to the differential equation. Nice thing about it is that it also explicitly separates our output, input in our system, so then we can formulate a transfer function. And when it comes to transfer functions, the transfer function is only dependent on the input response. So if we have our total response, we have our input response plus our initial condition response, also known as the natural response. We ignore the natural response when we're looking at the transfer function only. Today, we're on chapter 3 now. We're going to talk about state space. This is going to tie in with why we care about eigenvalues in our system. When we formulate our state space, we can then find our eigenvalues. And we're going to be talking about that. Am I sharing my screen? Yeah, I should be sharing my screen, but maybe I'll try sharing my screen again. Do you see my screen on my tablet right now? People online, can you see my tablet screen now? I still can't see it. Okay. Okay, both on each other into the lecture room. Okay. How about now? Can you see that? Here, I'll join through my tablet again, and maybe that'll fix that. Oh, I think I know what's going on. Let's try that. Nope, wrong one. Don't need that angle of my face. All right, how about now?
Yes, thank you.
Okay, thanks. Thanks for letting me know. Okay, so today we're on state space. This is chapter 3. We're going to be pretty much covering all of chapter 3 and the tail end of chapter 4, and then hopefully tomorrow we can start chapter 4, which is going to be on poles and zeros in first order and second order systems. Yesterday we talked about dynamic systems, and we use dynamic systems to, we model it using physics via free body diagram, and then we can formulate our differential equations. And then differential equations can be used to describe how the input and output of a system behaves. In our mass spring damper thought experiment, we can see that our acceleration is dependent on our velocity and our position and our input force. And we can see that our states, in this case, our states are velocity and position, are going to depend and determine, or are going to be related to our acceleration. And so basically, we started this for any arbitrary dynamic system. We can look at the state and change in energy. Think of state space as how we transfer energy from one state to another state, which then we use to project the future states. Think of it like that. And then here's the more technical definition: state variables of what state variables are. State variables is the minimum set of variables required to fully describe the system. Think of it in math terms, the smallest set of linearly independent system of variables. I'll go more in detail about what I mean by that. So then the way we formulate our state variables, think of it like this. If we're looking at a mass spring damper and we have acceleration on one side and then it's a function of position and velocity, then our state variables, I'm going to define it as x, is going to be equal to my position and my velocity. So then here then for x dot, we get x dot and x double dot. We're just taking the derivative of our state variables. And I know it's a little bit confusing because I'm using the x and then I have x here. So maybe I'll, in my notes, I tried to boldface vectors, but maybe here, since it's hard to tell, I'll just put a underline right here so you can see that it's a vector. And then, so this is basically a function of my state vector. And then this is our input. So in our previous example, force was our input. And when I'm talking about the smallest set of linearly independent system of variables on the previous page, x double dot, so the acceleration is a function of position and velocity, meaning that the acceleration is not a state variable because it's dependent on position and velocity. So as an example, if I have, let's say I have this differential equation x to the nth derivative. So this n here is just going to denote the derivative plus some constant a n minus 1 multiplied by x n minus 1 derivative plus all the way down to a1 x to the first derivative plus a0x is equal to our input u. So all of these variables u, x, they're going to be a function of time. I'm just dropping the t for now. Anyone want to guess how many state variables we have here? How many? One? A little bit higher. Not two either. So what's our highest derivative here? N, right? So we actually have n state variables. And it's not because we have n derivatives. If we count it, if we rearrange this, we can rearrange this equation as x to the nth derivative is equal to minus a n minus 1 x to the n minus 1 derivative minus a1 x to the first derivative minus a0x plus our input. So what we're saying here is that x to the nth power is linearly dependent on x n minus 1 all the way down to x to the first derivative plus x. So we have n minus 1 variables here, and then this is the last variable here. And we get n state variables. The input is not a state variable. Makes sense? So the highest derivative is not going to be your state variable usually. It's usually dependent on all of the other state variables because we can rewrite our differential equation in this form. So this x to the n derivative is linearly dependent on the rest of the state variables, just like how acceleration on the previous page was dependent on position and velocity. This is related to something called the Cayley-Hamilton theorem, if for you math nerds out there, probably for me. Basically, it's just saying that this has n state variables where the highest derivative is
dependent on all of the lower derivatives. And you'll hear about the Cayley-Hamilton theory in 547. Yeah. Any questions? Okay. So this is all a lot of definitions. We'll do some examples, which hopefully will make more sense on how um, we identify state variables. But before we do that, we had to talk about state space representation, which is the bulk of chapter 3. So basically, we can repackage a differential equation into a first order differential equation, like a first order differential matrix equation. I guess I should ordinary differential matrix equation. Yeah, that makes more sense. So basically, when we, in the previous problem, we had like an nth derivative differential equation. Well, we can put this into a state space equation, and then it becomes a first order differential equation in matrix form. So a state equation from the textbook, state equation shows the relationship between the current states, which is x of t here, in the input with its future states. So basically what's saying is that x dot, the derivative of our future states, is equal to our a multiplied by x, which is our current states, plus b multiplied by u, which is our input. I'll go over what each of these stands for. And then we use the state equation to predict future states. And then the output equation is used to extract our desired states. Y is equal to c times x plus d times u. U is just like a feed forward term. If we want our input to show up in the output, we have d there. So I have more, I guess, like more of a detailed explanation for what this means. So here's our state equation and our output equation. So this is our state space representation. And basically what we want to do is what A does is it describes how our states are connected. So it describes how they're interlinked with each other. Like, for example, how acceleration is related to position and velocity. And then B describes how the input enters the system and affects which states. So if we're pushing our mass in our system, B is going to describe how that energy is put into the system. C describes which states are measured in the output. So C is usually determined by our sensor limitation. So our sensors will tell us what it can measure, what it cannot measure. Some states are impossible to measure. So if I have a thermometer, I can only measure temperature. I can't measure change in temperature. So that's like a limitation. And then D allows the input to appear in the output. Usually it's not related too much in this class, but it's just for completeness and thoroughness, we should have the D equation in there. Yeah, so then we use state space A, B, C, D. So usually, in some research papers, they might do like parentheses, A, B, C, D. That's when they do that, that's referring to state spaces. And we use this to find the transfer function in the S domain. So in chapter 2, we can use the Laplace transform directly on a differential equation to get this system is equal to output divided by our input. We can now skip all of that and use the ABCD matrix to directly get our transfer function equation. So there's this equation here. It's called the state space to transfer function is going to be equal to our output C multiplied by our frequency domain S multiplied by the identity matrix minus A inverse times B plus D. So this is the equation that will get you the same exact transfer function. And in MATLAB, our command to do that is called SSTF. Oh, SS2TF. And then we put A, B, C, and D. And this is going to be in MATLAB. And this gets us our transfer function. I believe the output is going to give you the numerator and denominator coefficients. Any questions? And we'll go over an example on how to find the A, B, C, and D matrices next. Okay, so if we go back to that mass spring damper, and let's just draw it out again. And we have a dampener. Of K, our spring constant K, damping coefficient B, our input force is F of T, which is our input. And now let's say I'm measuring my position. We want X of T, the position, to be my output. So now that I specify which state I want to measure, we can determine our output equation as well. So first thing we want to do is we want to formulate our ordinary differential equation. Since I've done that multiple times now, I'm just going to give you the differential equation. Mx double dot plus bx dot plus kx is equal to f of t. So that's our differential equation. I usually like to rearrange this differential equation such that the highest derivative state, or the highest derivative, is going to be on the left-hand side, and then everything else is on the right-hand side. So I divide everything by m, and then I subtract bx and kx. So then we get minus k over mx minus b over mx plus f of t. So this is my rearranged differential equation. So then the next thing I want to do is I want to identify the states. And yeah, question? Oh yeah, I forgot. That's not. They are two different x's. Thank you. Okay. Yeah, how many states do we have in this equation now? Try again. Two. Yeah, exactly. It's because this is not linearly independent. It's dependent on position and velocity. So, and f of t is an input. It's not a state. Okay. So then that means position and are our states. These are states. So then when I put them in our state vector, it's going to look like this. You don't have to use that. You can also write your state vector like this. This is also valid too, if you want to represent it like that. Are you talking about f? Oh yes, thank you. 1 over f of t. I think I'll start bringing candy and giving you guys candy if you catch my mistakes. That's what my physics teacher used to do to help us pay attention in class. Maybe for Halloween. Yeah, question. You mean like the rank of how we rearrange our state vector? Yeah, it does. So yeah, usually we usually start with the lowest derivative and go higher. Yeah, this is the standard. Yeah, I'll write it down. Start with the lowest derivative. Yeah. The lowest derivative. Y, x, and x dot are the states. Um, So you're not sure why x and x dot are the states and not why x dot double dot is a state or is not a state. It's because x double dot, well, the way I think of it is that we can get x double dot by taking the derivative of x dot, and then we can get x dot by taking the derivative of x. Hmm. I think like it's more, are you talking about more of an intuition, not in terms of math?
I think it's more like an arrangement of the equation, right?
Right.
Bode back again, and expanded.
Yeah. Yeah. The way I just think of it is that because this is dependent on x and x dot, but I guess there's no equation for x dot is equal to x or something like that. That's how I think of it. I've never really questioned it, to be honest. But the reason why I just think of it is it's always that x dot is equal to your function of your current states plus your input. Like maybe not even your input, it's just usually of your current state. I mean, yeah, input in your initial conditions. So then that makes it such that you can't have a higher derivative in here with a lower derivative here. You can't have a higher order state, like high derivative state here with a lower order, like lower derivative state on the left hand side. That just makes it impossible. So it's like saying I know the future without before the past kind of deal. Maybe in terms of discrete time systems where you do one step ahead is based off of your previous steps, ax or ak plus b u of k. You can't have the other way around where you can't estimate what your next step will be without your current step, where you can't know what your current step is based off of your future step. I mean, you can, it's called a feed forward system, but then that's outside of the scope of this class. But in this case here, I think of it like this, more in discrete steps, where based off of my current step, I know where the most likely, the most likely next step will be. So it's the same reason why x double dot is dependent on the past states. In this case, it would be something like this, where we would say x k plus 1 is equal to minus k over m x k minus 1. I mean, it's not exactly the same, but it'd kind of be like this. Something like that. It's not exactly the same, actually, but I'm not sure if that's satisfactory. But maybe we can talk about that after class or in office hours. Yeah, another question.
It's very late in the class to ask this, but I'm assuming every system that we're going to is describable by a linear.
Yeah,
Like
everything is going to be linear. All of the matrices we're working with, like the A matrix that we're going to formulate, will be full rank as well.
oh, okay,
So everything's invertible. Yeah. Yeah, there will be special cases where it's not invertible, not covered in this class. We're just going over foundation stuff first. Yeah. No worries. You're good. One other thing that is we can also actually represent our state variables like this. Because there's actually infinite ways of describing state variables. We can describe it as, let's say like x dot minus 1/2 x, and then have x here, or x plus 2x dot. These two are variables that are independent of each other. Yeah, another question.
I remember we knew the amount of state spaces because it was the highest order minus 1 times the degrees of freedom.
So minus the highest order. So like, let's say in this case, it's 2. Or no, it's
so it'd be like, because it's X, the second order.
Yeah.
there's
Oh, there's 3. So -1. So that's 2. The degrees of freedom.
two masses spring to the right of it.
Mm-hmm. Kind of like a well, actually one of the homework problems has this, right? Yeah, there's 2 masses. Yeah. So then we have the highest order, which is 3 minus 1 is 2 multiplied by 2 degrees of freedom, which is 4. Yeah. This is a 4 by 4. Yeah, actually, I like that. So I'll write it down. So it's going to be your number state variables.
We didn't get into super complicated ones, but
Yeah. It's equal to, yeah. Well, I'll just write it down for now. Highest order. All right, if it's wrong, I'm going to pin it on you. -1 multiplied by degrees of freedom. So
Then the highest order times instead of -1? Because you guys said there were 3 terms.
so right, but the thing is, our highest order here is, so it's the number of, it depends on how you define highest order, because here he's saying that there's highest order is 3 because the 0th derivative, I guess, is the first order, but maybe highest order derivative instead. Derivative. But it might not be the highest order derivative. Actually, yeah, I think it is the highest order derivative. Times degree of freedom. Stick with that for now. Let me check that. All right. So we're going to ignore this part. We just started. So, well, yeah, you can write like that on the right. Standard approach is to start with the lowest derivative or the lowest state and then go up. Like this is the order we go in increasing derivative. Okay, so then what we have to do now is we plug it into our state space equation. And for our state space equation, I'm going to write it out again. X dot is equal to AX plus BU. And then Y is equal to CX plus DU. Okay, so then I'm going to write X dot. X dot is equal to X, the derivative of X, which is X dot. And then the derivative of X dot, which is X double dot, is equal to, our A matrix is square. It's a 2 by 2 because we have 2 state variables. Our B matrix is, for SISO system, is a column vector multiplied by our input, U, which is, in this case, f of t. Okay. If you look at this matrix form here now, it's basically just 2 linear equations stacked on top of each other. We'll start with the second row, x double dot, because we have that equation here. What's going to be in this bottom left column? Yep, minus k by m. Is that too small? Okay, I think that's okay. And then the bottom right is going to be minus, yep, b by m. What's going to be in our input right here? Yep, 1 over m. Okay, now let's go to the top column. X dot is equal to, what's going to be in the top left? 0. Yep. Top right? Yes, exactly. So the top row is just basically a redundant equation. We're saying velocity is equal to velocity. So then we have 0 there. And that's our A matrix. This is our A matrix, and this is our B matrix. Okay, So then y is going to be equal to, and because I only specified one state, I want the position to be the output. It's going to be a single output, so it's just a constant, or not a constant, it's a 1-by-1 system. This is Cx plus du. No, I'm gonna just put a 0 there because we don't have our input showing up. For our position, what do we need in this row vector? Yep, 1, 0. Thank you. So that's it. That's our C matrix. And then that's our D matrix, or constant in this case. Okay, so let's say if we want position, or if we want velocity, if we want y is equal to x dot, then we're going to choose 0, 1 instead for our C matrix. Because then we're just multiplying 0, 1 with x and x dot to get x dot as the output. So depending on what I ask you for the output, that's how you're going to choose your C matrix. So if I want, let's say if I want y is equal to x plus x dot, for no practical reason, but then you're going to choose C is equal to 1, 1 here. So this is more designer choice. And sometimes it's sensor choice too. Your sensor is going to be limiting what you can measure. So then you're going to formulate your C matrix based off of what sensor you pick. Okay. So now we can, now we want to get the transfer function. Because we don't have the input showing up as the output. So when I say I want the output to just have position only, then D is going to be 0. But if I say I want the output to have the input command too, then D will no longer be 0. Yeah. But we don't really need that because we usually know what input we put into these systems. So we don't need that to show up in the output. Okay, so now we can apply the state space to transfer function equation. And that equation is going to be g of s, our transfer function, is going to be c times s I minus a inverse b plus d. Oh man, I'm running out of space. Okay. And if I just plug these in, we get 1, 0 multiplied by si minus a. So it's going to be, we're going to just be subtracting a from s. So we have s in the diagonal columns and we're subtracting a. So we get minus 1 plus k over m and plus b over m inverse multiplied by 0, 1 by m plus 0, which is our D matrix. Okay. A little side note about our, I hope I have enough space. If I have a this is only for a 2x2 matrix. The inverse of a 2x2 matrix is going to be the determinant of this matrix, 1 over AD. Let's see. It's AD minus CB, right? Yeah, it's AD minus CB multiplied by the diagonals where you're going to change spots. So A becomes D, D becomes A. And then the off diagonals are multiplied by -1. So that's the inverse of a 2x2 matrix. So we're going to do that here. We're going to apply that. And it's going to be equal to 1, 0, 0 multiplied by, or I'm going to pull the determinant out. It's going to be the determinant of this is s squared plus b over m s plus k over m multiplied by 1, 0 multiplied by, oh my God, I'm running out of space. S plus B over M. Oh, I hate. All right, I'll create a new page. Sorry for moving stuff around. All right, now that we have more space, we're going to swap the diagonals. S plus B over M. S in the bottom right diagonal minus K over M minus 1 multiplied by 0, 1 over M. I made a grave error. This should be a positive one. There you go. All right. So before I do this matrix multiplication where I multiply this out, we can save a step. We see that there's a 0 here and there's a 0 here. So that only leaves us with one option, which is when we multiply this out, we'll actually only be getting this term multiplied with, I'll do a different color instead. We're going to get this term multiplied with this term left, because this is going to wipe out the second column. This is going to wipe out the, this is going to wipe out the bottom row. This 0 right here is going to wipe out the first column, I believe. So anyway, if we multiply this all out, we just end up getting 1 over M divided by S squared plus B over MS plus K over M. And this is going to be equal to our output divided by U of S. Any questions? All right, well, we're not done with this example yet. Okay, so what I want to do next to kind of review Laplace transform is we're going to determine the output response now. Now that we have this equation, let's make everything 1. K equal to 1, mass equal to 1, damping coefficient equal to 1. Okay, let's determine the output response. Find the output response for a unit step input. Output response for a unit step input where U of S is equal to 1 over S with 0 initial conditions. Okay. All right, so let's rewrite this equation here where we have the output is equal to our transfer function multiplied by our input. Y of S is equal to G of S multiplied by U of S. So then we can plug in U of S. We can also plug in G of S. Since everything is 1, we get this equation 1 divided by S squared plus S plus 1 multiplied by our unit step input. Okay, so the nice thing is we don't have to take the Laplace transform. We can just take the inverse Laplace transform of this equation here. Basically, what we want to do is we want to take the inverse Laplace transform of Y of S to get Y of T. But the problem is that this form right here, it's not something we can look at our table and find the solution to. We have to take the partial fraction expansion and get this into a form that we can recognize, and then we can apply our inverse Laplace transform table. So we're going to take the partial fraction expansion. And that's going to get us basically 1 over s multiplied by s squared plus s plus 1 is equal to, let's see, k1 over s plus k2s plus k3 over s squared plus s plus 1. We use this form because s squared plus s plus 1, the roots are going to be complex conjugates, so we can't expand s squared plus s plus 1 further, or we can't factorize it further. Okay, so we can find k1 by saying the limit, like multiplying everything by s and saying the limit of s going to 0, but instead, because there's only 3 variables, I'm just going to multiply everything by the common denominator, which is s times s squared plus s plus 1. So I'll multiply both sides by s squared plus s plus 1. Man, my s's are looking like 5s. Also, another mistake on exams. S's can sometimes look like 5s. Do not mistake them for 5s, please. Okay, so when you write your s's, be extra vigilant on the curves. Okay, there are times where I can tell people are rushing and their s's were mistaken for 5s or the other way around. So just be careful. I just saw that. I just remembered. Okay, so we get 1 is equal to k1 times s squared plus s plus 1 plus k2s squared plus k3s. Then we're going to group them together by their powers. 1 is equal to k1 plus k2s squared plus k1 plus k3s plus k1. And then we can just basically solve for k1, k2, and k3. We can see that k1 is equal to 1 here. And then we can also solve for k2 and k3, and they so happen to be equal to -1. All right, so now we can plug this back into our partial fraction expansion. Y of s is equal to 1 over s plus minus s minus 1 divided by s squared plus s plus 1. Okay, so now that we're back to this step, it's going to be a little bit easier taking the partial fraction expansion of this. Well, at least for this term, that's a unit step input. So when we take the inverse Laplace of unit step, it's just equal to 1. So that's easy, but this one doesn't look like anything on the tables, right? It looks different. Let me pull the tables up. I think I have it from yesterday. Oh, I hope I have it. Oh, I only have 2 of the properties. All right. I'm going to pull the tables here, so it's a lot easier to see it. Do I have the exam reference? Yeah, we'll just grab that. Probably shouldn't be recording this. All right, there you go. Although, I mean, I'll give you this last year's exam or your final exam practice, so it's not like it's a secret. see, that's the wrong table. There you go. I need that table. Actually, I need both tables. So this problem requires both tables. Oh, we got so much left. Wow. Okay. All right. Hopefully this will make it a little bit easier to follow. Basically, what we're trying to do is we need to get this right-hand term, this minus s minus 1 plus s squared plus s plus 1 to look like something on table 2.1. And right now it doesn't really resemble anything, but maybe let's just look at minus s minus 1 divided by s squared plus s plus 1. And actually, let's take out the minus sign. We can pull out the minus sign here instead. Okay. We can actually split this up into s divided by s squared plus s plus 1 plus 1 over s squared plus s plus 1. And if we look to table 2.1, it kind of looks like property number 6 and 7, right? Where we have omega right here and we have s right here. So now we can see that this response is going to have some sine and cosine components in it. And it makes sense. It's a mass spring damper system. You hit it with a constant input, it's going to oscillate a little bit before hitting steady state. So there's going to be some sine and cosine components into it, like in this, but it doesn't resemble that table yet. And the reason why is because we have this term here, this s term. So it's going to sound a little bit like hand wavy, but basically what I want to do is I'm going to replace this s with another s using the substitution method, which you can see in property 4, I guess. We're going to be using property 4. And hopefully it'll make more sense, but I'm just going to, instead of writing it like this, I'm actually going to write this equation like this. S plus 0.5 minus or plus 0.5. So I'm going to split the 1 in half. And we can actually rewrite this bottom equation as s plus 0.5 squared plus 0.75 so the top and bottom equations are the same. And is this okay so far? Okay. You've seen why I'm pointing at property number 4 in table 2.2 now? Yeah. Because now we have this a term here is going to be equal to 0.5, and we can pull that out as an exponential. Okay. And this is called the frequency shift. Frequency shift. Yeah, you have a question?
Example video, you did the frequency shift, you mentioned it, but I wasn't sure if it's because on the numerator of the first term it has the s plus a, or if it's because in the denominator there's that squared s plus a.
So yeah, to find it, you actually have to do this frequency shift in the denominator first. then based off of that, you apply that to the numerator. Yeah, because then whatever, like, let's say this was s plus 2 on, it's actually 1120, but let me just wrap this up real quick. If it's s plus 2, then we do it like that, because we can always manipulate this numerator term by pulling a constant out to getting it to the right omega value. So yeah, so we would actually do this first step. This is first. Find this first. So we're going to wrap up this example tomorrow and finish chapter 3 and start chapter 4 tomorrow. And yeah, I'll upload this. It's not done yet, and I'll upload a complete set of notes tomorrow. And so that way you can look at this today.